Hello there, everyone watching. My name is Oscar Pio. Today I'm making the final presentation for the machine learning project, that is machine learning approach to database risk prediction and extreme label scarcity based on semi-supervised and positive-unlabeled learning. So let's take a look at our quick presentation roadmap. So basically, we shall look at background introduction, shall look at problem statement, research questions and objectives, research methodology, all the way through practical recommendations, future work and acknowledgements. So let's have a good understanding of our background and where we're coming from. So we see diabetes mellitus is a chronic metabolic disorder affecting over 537 million adults globally, and we see that by 2045 there's a projection that it will exceed 700 million. So however, another thing we see that is traditional screening relies on biochemical tests such as HbA1c and fast blood glucose, which are often inaccessible in low resource environments. So, and we normally see that there are basically three label scarcity scenarios that arise. One is that we find that there are no labels at all. So in that case, what do? We use that is unsupervised learning. And then sometimes we find that there are few labels, so we use semi-supervised learning. Then sometimes we find only positive labels. So in that case, we use positive-unlabeled or PU learning. So what's our problem statement? So our problem statement in this case is that is in low resource regions, many individuals or persons with diabetes remain undiagnosed due to limited access to clinical testing. And we see that symptom-based screening could enable early detection, but predictive models must be robust to reality that most patient records lack confirmed labels. And then what drives our research? That is our research questions and objectives. So the questions, we have basically 4 research questions and 5 research objectives. So the first question is that can unsupervised learning identify patient subgroups linked to diabetes risk? Then 2, we also want to find out if semi-supervised learning outperform our supervised baseline when only a fraction of labels are available. We also want to find how effective PU learning is in detecting hidden positives when only positive cases are known. Then lastly, we also want to find out which paradigm is optimal under the different label availability scenarios that we have already looked at. So, and then our objectives, 1, that is basically we want to perform that's exploratory data analysis with at least quite a number of visualizations. Then if I go to the last, that is we want to compare all the approaches and derive practical recommendations. Now, for every research or for every project that you undertake, there must be a methodology or a structured approach that you follow. In this case, we come to our research methodology. So basically, it is a 6-step approach, and of which we begin with the data loading all the way through interpretation, but in between we have data pre-processing, exploratory data analysis. In this case, that is EDA. Then data modeling, where we perform modeling. Then evaluation, that's where we get to evaluate which model performs best or better than the other under what scenario, and based on which detail of which we shall take a look at it in great details. Now let's first understand our data set or the data we are dealing with. So basically we have that is a sample of, we have that is 520 records. Then we have 17 features, that is 8 gender and 15 other features to make 17. Then classes, we have that is positive, that is 60%. Then negative, that is 40%. Then fortunately, we do not have any missing value. Then the split protocol, that is PU aware stratified. Now let's look at the univariate analysis. Now this is where we are. Now we are under EDA, that's expert data analysis, where we get to see the distribution, how these features contribute or contribute to diabetes. So when you look at, we took a look at age, where we saw that age almost has a normal distribution with diabetes. sometimes you find that distribution is left skewed, or sometimes distribution is right skewed. So if you have done probability, let me say at advanced level, that's in Uganda, then probably if you're doing statistics as a degree, then you should have a better understanding of what a normal distribution is. But still, with or without that, you can still take on other statistical courses available online, using available resources. So that's basically our invariant analysis. Then also when we also look at how gender distribution with the, let me say, with the sex, with the gender, we see that male takes, that is 63.1%, and then female takes, that is 36.9%. Then the bivariant analysis, here we look at, that is bi means 2. We look at how 2 features all contribute to diabetes. And then now we also go ahead to look at as pair plot of top 5 most predictive features. So this all under visualizations. Now still here we are looking at visualization continue, that is we're looking at age, where if you take a look at this, if you look at how my cursor is moving, you can see that almost this follows a bell-shaped curve, or a normal curve. Then let's look at now the unsupervised learning methods. So basically the methods we consider are k-means clustering, that is GMM, that is Gaussian mixture model, DB scan, and then hierarchical clustering, and then the evaluation metrics, basically that is Shiller score, then ARI, that is adjusted run index versus true label. So those are basically the methods we looked at. That's unsupervised learning. Then semi-supervised learning, we look at quite a number of algorithms where we looked at, that is label propagation. So where kernel affinity matrix propagate, then let's look at that, in this case progress label through graph structure, then had assignments. Then label spreading, enhanced version with the alpha parameter, that is 0.5. Then normalized graph Laplacian, then more robust to noise. So in this case, what's the process followed? So in this case, we build similarity graph between all samples, propagate known labels to neighbors, iterate until convergence. In this case, the evaluation, that is performance measured based on unlabeled portion only. And then positive unlabeled learning methods. So in this case, the goal is to detect hidden positive when only positive labels known. So in this case, we basically use, that is fixed 50 label positives, that is 2-step PU, and then PU bug, of which it was our champion. And then the evaluation, in this case accuracy, was based on unlabeled data. And then hidden positive detection rate, in this case was a critical metric. Then now let's look at the evaluation metrics and baseline later. So why symmetric accuracy is misleading? So we find that a model discovering hidden diabetes gets penalized for false positives. In this case, what do we do? So there's need for precision recall focus. And then the primary metric, in this case, that is PRAUC, precision recall under area curve. And then minority class sensitivity recall, that is true positive recovery rate. In this case, the levels are naive, semi-supervised, and then proposed. Then the methods respectively are supervised RF, label spreading, then PU bugging. Then the assumptions respectively are, that is all unlabeled, that is negative, graph-based propagation, and then models label contamination. And then results of semi-supervised learning, here you can see. So k-means, that is with the k of 3. If you look at the Shiller score, and then ARI score, and you compare, so we can see that DB scan, that is higher Shiller score but low ARI. So, and you see that density based versus true clusters. I'm a bit fast, it's okay, you'll bear with me. So then results, that is for unsupervised learning. So in this case, what happens that we see that with the cluster of 0, 1, 2 respectively, and size of 210, that's 210, 175, and then 130, 135. Then die-based rates respectively of 85%, 45%, and then 10%. Then the top symbols for cluster of 0, that is polydria, and then polydestia. And then with the cluster of 1, the top symptom weakness and fatigue. Then with the cluster of 2, the top symptom, in this case we see that there are basically few symptoms. And then what's the interpretation? We see that unsupervised learning models, unsupervised learning reveals clinically meaningful subgroups without labels, and labels, that is with ARI of 0.42. Then results of semi-supervised learning continued. So we see that at 10% level, semi-supervised learning gives us, that is accuracy of, that is 84%, with the supervised learning of 73%. Then at 33% level, semi-supervised, that is accuracy of 91%, and then supervised of with accuracy of 86%. Then what at 50% labeled, we see a narrow gap, that is of 94% versus 91%. And then our key finding in this case is that semi-supervised learning outperforms supervised by 8%, with same 20% label data successfully leverages unlabeled patients to improve decision boundaries. Then results, that is PU learning. So basically in this case, the key finding is that PU bugging achieves 92% accuracy on unlabeled data and recovers 94% of hidden positives. And why PU bugging works is in this case that bootstrap samples creates diverse negative tests, and each tree sees different noise and sample averages it out. So that is it basically for PU learning. Then the comparative analysis, we see that is PU learning, semi-supervised learning, unsupervised learning, and then supervised with 20%. So we see the best method with PU learning, that's PU bugging, then with accuracy of 0.92%. Then semi-supervised learning, the best method is label spreading with accuracy of 0.89%. Then unsupervised learning with the k-means with accuracy of 0.42%. Then supervised learning with random forest, that's the accuracy of 0.81%. Then Oracle upper bound, random forest, that is accuracy of 0.97%. Now let's look at the deployment and edge execution. So how do you go about this? So this is what happens. On interface, the user puts in the inputs, that is basically the symptoms. Then the model does the processing. Then after doing the processing, it goes ahead to do the risk probability plus recommendation, and then we see a badge display, just like in a separate video I recorded a demo of how this works. So I recommend you take a look at that of this. Then you find that it definitely matches with our deployment and edge execution. Now let's look at knowledge distillation. So this is a technique where a large teacher model trains a smaller model in quote by sharing its soft probability predictions, preserving accuracy while drastically reducing model size for edge deployment. So in this case, we can see that here we have, that is a teacher model as a random forest with a size of about 126 kilobytes with accuracy of 56.5%. and F1 score of 0.678, and then in this case the logistic regression, which is the student model. So this gives with a size of 2 kilobytes, accuracy of 55.1%, and F1 score of 0.66%, which is relatively close. Yeah. So but in this case, the key idea is that the student learns from the teacher predictions, not raw labels, gaining richer interclass knowledge. So here we still go ahead to expand on that. That's the teacher versus the student model, where on the left we have the random forest, and on the right we have the logistic regression. So that's basically that. So still we go ahead to explore how this works stepwise, where we have the step 1 where we train the teacher, then step 2, that is generate soft labels, step 3 we go ahead to train the student, and then step 4 to deploy deploy the model. So what are the advantage of this? One, we see that there's size reduction in our model, and then 2, there's accuracy retention, then 3, F1 preserved, and then 4, model ready. In this case, that is for with the offline capabilities and ARM tablets. So that's the benefits of knowledge distillation. Now, of course, for any research or for any project you're undertaking, there must be limitations and ethics. And in this case, our limitation was data scope and validity. In this case, our data size was 520 records. And then potential confounding. This is where the effect of confounding variable comes into play. And then symptom encoding, where we see that symptoms are encoded as binary yes or no, or true or false, or Boolean, which simplifies the clinical reality. So in this case, these critical nuances such as symptom, duration, intensity, frequency are not captured, potentially overlooking fine-grained predictors of disease regression. And then for ethical deployment, so that these models are designed for clinical decision support, not autonomous diagnosis. So deployment requires strict clinician oversight, informed patient consent, and robust data privacy protocols to ensure algorithmic fairness and patient safety. Then practical recommendations. So in this case, for the different scenarios, we give different recommendations. So for only positive labels available, we recommend using PU bagging. And then for a few labels that's under 30%, we recommend using semi-supervised learning. And then when there are no labels at all, we recommend using unsupervised clustering with exploratory insights. And then when we have all labels, then it is recommended to use supervised learning, that is with the upper bound. And then future work, that is set expansion. And then fairness and bias audits. Then that's calibrated models. And then lightweight deployment. And then prospective clinical validation, that is deploy the best performing supervised model in clinical workflow, in real clinical workflow. Compare model predictions against clinician diagnosis in real time to validate utility and impact on decision making speed. Then these are quite a number of references or resources we used. You can take a look at them or find out about them. And then also here to bring this to a conclusion, I want to really acknowledge our research team, that is me, Oscar Opio, then Babiri Sandra, Richard Ogwal, and then most importantly our instructors or our lecturers or professors, that is Dr. Eunice and then Dr. Marvin, for being there for us every time, giving us corrections here and there, giving us guidance. We really appreciate. And also we give accreditation or acknowledgement to our institution, that's Makerere University, for the support granted to us through our instructors. So thank you so much for listening. In case of any questions, I'm available. You can reach out to me, and I'll be glad to hear your feedback. Thank you so much.